How much do you know about the sun's power? What if that incredible power source, nuclear fusion, wasn't confined to distant stars? Consider a world where fusion began spontaneously within Earth. One day, you go outside and everything has changed. The notion of natural nuclear fusion taking place on Earth sends chills through scientific circles. The conditions needed for hydrogen atoms to overcome their electrostatic repulsion and fuse into helium, releasing immense energy, are extreme. We speak of temperatures in the millions of degrees Celsius and colossal pressures, conditions found within the cores of stars like our Sun. On Earth, these conditions simply do not arise naturally in a sustained manner. Our planet's core, while incredibly hot and under immense pressure, is primarily iron and nickel. It is the immense gravitational forces within stars that create the necessary confinement and temperature for fusion to ignite and persist over eons. The sheer mass of a star provides the gravitational pull needed to contain the incredibly energetic plasma generated by fusion. Earth's gravity is insufficient for such a feat under normal circumstances. So, let us hypothesize. Let us consider a scenario, perhaps initiated by an unforeseen geological event. Maybe a massive impact event that somehow compresses a specific region of the mantle to an unprecedented density, or an extremely rare concentration of radioactive decay in a localized area generating unforeseen heat. Or consider an incredibly localized anomaly, perhaps a previously unknown form of exotic matter interacting with ordinary matter in a way that triggers fusion. In such a situation, a pocket of deuterium and tritium deep within the Earth's mantle or crust might somehow attain the critical temperature and immense pressure for nuclear fusion to commence. First, observe the initial ignition. It would not be a planet-wide explosion like a nuclear weapon, which relies on fission. Instead, it would likely be a localized, intensely hot region, perhaps only a few meters or kilometers in diameter initially. If this occurred deep within the Earth, several kilometers below the surface, the immediate consequences would be dramatic and largely unseen at the surface initially. The surrounding silicate rock, under immense pressure, would instantly vaporize, transforming into superheated plasma, an ionized gas where electrons are stripped from atoms. This would create a rapidly expanding cavity, pushing outwards with tremendous force. Then, the immense energy released, far exceeding that of any conventional geological process, would begin to propagate outwards as shockwaves through the solid Earth and as intense heat radiating through the surrounding material. Depending on the scale and location of the fusion event, this could trigger significant seismic activity. The initial shockwaves could generate earthquakes of magnitudes never before experienced, potentially registering well above 10 on the Richter scale, or its more modern counterparts, like the moment magnitude scale. Consider the ground beneath your feet violently shaking, not just for minutes, but potentially for hours, as the immense energy dissipates and reverberates through the planet's crust and mantle. Buildings, even those designed to withstand significant seismic activity, would crumble under such unprecedented forces, and the very structure of the landscape would be dramatically altered, with massive fault lines appearing and existing ones reactivating with extreme intensity. Landslides and tsunamis of unimaginable scale could be triggered. Next, if the fusion event occurred closer to the surface, perhaps within the upper crust at a depth of only a few kilometers, the effects would be even more immediate and visually stunning, albeit terrifying. View a patch of ground suddenly glowing with an unearthly light emanating from the superheated plasma below. The air above would shimmer and distort due to the extreme temperature gradients. Rocks in the immediate vicinity would not just melt, they would be vaporized and ejected as incandescent projectiles. Consider the surface temperature in that localized area suddenly rivaling that of the sun's surface, capable of instantly incinerating anything in its path. The intense thermal radiation would spread outwards, causing widespread fires and posing an immediate and lethal threat to any living organism within a significant radius. Consider the composition of the Earth. While hydrogen is the most abundant element in the universe, it is relatively scarce in its pure or isotopic forms within Earth's crust and mantle compared to heavier elements like oxygen, silicon, and iron. For a sustained fusion reaction, a significant amount of fusible material would be required. If the initial event occurred in a small, isolated pocket of deuterium and tritium, it might consume all available fuel quickly, resulting in a short-lived, albeit catastrophically intense phenomenon, leaving behind a vast cavity of superheated rock and a landscape scarred by the immense energy release. However, let us consider a more sustained scenario, perhaps involving a continuous, albeit slow, supply of deuterium and tritium being drawn into the fusion zone through geological processes we do not currently understand. First, a localized area of intense heat and pressure would persist, potentially growing in size as more fusible material is drawn in. This underground sun would radiate energy outwards through the surrounding rock, causing widespread geological upheaval on a global scale. The increased heat flow from the Earth's interior would destabilize tectonic plates, leading to a dramatic increase in seismic activity worldwide. Existing volcanoes would likely erupt with unprecedented force, releasing vast amounts of ash and gases into the atmosphere, potentially triggering a volcanic winter. New fissures and volcanic vents might open up in unexpected locations, spewing molten rock and toxic gases like sulfur dioxide and carbon dioxide into the atmosphere, further altering the planet's climate. Then, the Earth's magnetic field, generated by the movement of molten iron in the outer core through a process known as the geodynamo, could be significantly affected. The intense energy release and the massive shifting of mass within the planet's mantle and crust could disrupt the delicate convective currents in the outer core that drive the geodynamo. If the magnetic field weakened significantly or even temporarily collapsed, the Earth's surface would be bombarded by high-energy charged particles from the Sun, dramatically increasing radiation levels at the surface. This increased radiation would pose a severe threat to all forms of life, damaging DNA and increasing the risk of cancer and other radiation-related illnesses. Communication and navigation systems relying on satellites and radio waves would also be severely disrupted. Next, the oceans, which cover over 70% of the Earth's surface, would begin to feel the profound effects of this internal upheaval. The increased geothermal activity, particularly along mid-ocean ridges where new crust is formed, could lead to a significant and rapid rise in global ocean temperatures. This warming would have devastating consequences for marine ecosystems, causing widespread coral bleaching, disrupting food chains, and potentially leading to mass extinctions of temperature-sensitive species. The warmer water would also contribute to more intense and frequent extreme weather patterns, fueling stronger hurricanes and typhoons with higher wind speeds and greater rainfall. Coastal regions would experience more severe flooding and storm surges. Consider the delicate balance of ocean currents, such as the Gulf Stream, being thrown into chaos by the altered temperature gradients and increased freshwater input from melting ice. Consider your proximity to the coast. The sea level might rise not just from the accelerated melting of polar ice caps and glaciers, but also significantly from the thermal expansion of the water itself. Warmer water occupies a larger volume. Coastal cities and low-lying island nations could face unprecedented and potentially permanent flooding, displacing millions of people and rendering vast areas uninhabitable. However, an observer at a safe distance, perhaps stationed on the International Space Station, would witness a different, equally dramatic view of our planet. They might see localized hotspots on the Earth's surface, glowing intensely in the infrared spectrum, indicating areas of extreme heat emanating from below. They might also observe a significant increase in volcanic eruptions around the globe, with massive plumes of ash and gas reaching high into the atmosphere. Unusual atmospheric phenomena, such as intense electrical storms and auroras appearing at lower latitudes due to the potentially weakened magnetic field, might also be visible. The Earth might appear to be convulsing, breathing in a chaotic and violent way, a stark contrast to the relatively stable blue marble we are accustomed to seeing. Consider the stark comparison to geothermal energy we currently utilize. We tap into the Earth's natural, relatively stable heat to generate electricity in certain geologically active regions. Now consider that heat source being amplified exponentially, localized pockets of energy outputting magnitudes greater than any volcanic eruption. It would be like going from harnessing the warmth of a hot spring to trying to control a miniature star contained within the Earth. The scale of energy involved is almost incomprehensible, and the potential for catastrophic failure would be ever present. The Sun, a giant fusion reactor, has a gravitational field 28 times stronger than Earth's, allowing it to contain these immense forces. Earth lacks that crucial gravitational confinement, making any natural fusion event inherently unstable and dangerous. The consequences for life on Earth would be profound and likely lead to a major extinction event. The rapid and unpredictable changes in temperature, extreme seismic activity, increased radiation levels, and drastic alterations to atmospheric and oceanic conditions would create an incredibly hostile environment. Many species, unable to adapt to such rapid and extreme changes, would face extinction. Food webs would collapse and biodiversity would plummet. Human civilization, with its complex infrastructure, reliance on stable agriculture, and densely populated urban centers, would face an existential crisis of unprecedented proportions. Consider the complete disruption to global communication and transportation networks, the collapse of agricultural systems leading to widespread famine, and the potential for societal breakdown as resources become scarce, and the environment becomes increasingly perilous. First, essential services that we take for granted, such as power grids, water purification and distribution systems, and communication networks, would be severely and likely permanently impacted by widespread earthquakes, volcanic eruptions, and the general instability of the planet's surface. Then, agriculture, already facing challenges from climate change in 2025, would be devastated by extreme weather events, volcanic ash-blocking sunlight, and drastic shifts in climate patterns, leading to global food shortages and widespread famine. Next, the breakdown of societal order, driven by resource scarcity, environmental catastrophe, and mass displacement, could lead to widespread conflict, lawlessness, and the collapse of organized human civilization. View the vibrant and eerie glow of the aurora borealis, usually confined to the high-latitude polar regions, suddenly appearing across the entire globe, a constant reminder of the weakened magnetic field and the increased bombardment of harmful solar radiation. While visually stunning in a terrifying way, it would be a constant harbinger of a dangerous and increasingly uninhabitable environment. Very soon we will take you on your next hypothetical adventure, exploring what might happen if Earth suddenly gained a second, smaller moon, and the gravitational chaos that would ensue. Stay tuned for more thought-provoking scenarios.